Hey everyone. So to illustrate the use of linear transformation in regression, we're going to go through one of the examples that is provided in the textbook, which is focusing on predicting people's salaries, yearly earnings using survey data from 1990. And here's a quick data overview. We loaded our CSV. And all we did here was we also recoded a new gender variable that transforms basically the indicator variable male here to an index for female and male just as a factor, just for plotting purposes later on. So that's all we're doing in terms of kind of recoding and cleaning these data. Then looking at the table itself, we have 1,816 observations. Again, this is survey data from 1990, and we have 16 different variables, although we're not going to look at all of those right now. Particularly what we're interested in this example is we're trying to predict earnings. Here, that's the variable earn. And we will look at predicting earnings based on height right here, and gender. So we're looking at both a gender gap in earning or in salaries essentially in the 1990s, but we're also looking at height as a predictor. And the reason why we're focusing on height is again to also emphasize this as an example where we can have a predictive task, and we can make comparisons between people with different heights, but obviously we shouldn't attribute a causal interpretation on whatever coefficient we estimate for height as an effect of height, increasing height, people's height by 1 inch, causing an increase in salaries. Obviously, increasing someone's height wouldn't increase the salary. So we can't make this causal claim, but we nevertheless can think about these as descriptive comparisons in a predictive kind of framework, okay? So always keep in mind kind of these different interpretations, and we're only focusing on predictive tasks for now. We'll turn to causal claims and modeling for causal inference later towards the end of the semester. Okay, so this is the data overview. We are not using a lot of the other variables, but as you kind of follow along with this code, feel free to play around with some other measures, some other predictors, maybe changing some model specifications, and so on. Okay, I'm just going to show you the most basic specifications in this video. Okay, so the first thing we want to do is we want to model or predict earnings in dollars based on gender and height. Height is measured in inches. Earnings are measured in dollars. That's yearly earnings, so yearly salary essentially. And we're going to model this interaction between gender and height without any transformations, so just using the raw data. Okay. As always, we're going to use stan_glm for basic linear model. Earning is our outcome measure. Height and male are our predictors. We're going to use those without any transformation whatsoever. And we directly look at the regression output, the estimated coefficients, and we see first of all, the first consequence of the scaling. Remember that the outcome measure is income that's yearly income in dollars. So all our estimates are incredibly large because the income ranges around probably 20, goes up to like 50,000 or 100,000, depending on the type of sample of yearly salaries. So obviously we have huge coefficients both for the intercept and for our actual slope coefficients. Okay, we also observe a couple of maybe surprising results, from a naive perspective. One thing, for example, is that we have this negative coefficient for male, which, if you're not careful about the underlying scaling, might lead you to believe that, oh, actually there is no, women's pay gap, in the sense that women have, lower salaries than men, because obviously this suggests that men actually have a lower salary. Obviously, that's not the case, and we'll see in a second why that is a false conclusion. Um, um, because ultimately, this negative coefficient is a projection outside of the range of observations that we actually have included in our dataset. Okay, so obviously, as we look at these coefficients, um, um, even if we had a fairly good fit or fairly accurate predictions, we can't directly interpret these coefficients, right? The intercept minus $9,000 is obviously nonsensical, because this is the expected outcome for people with a height of 0 inches, which obviously doesn't exist. The kind of increase for 1 inch increase in height among women, so for male being equal to 0, we have a $401 increase in earnings. So this is potentially at least still interpretable. I already talked about kind of this coefficient for the dichotomous indicator, which is again not interpretable due to the fact that this is for height being equal to 0, and then we have this interaction effect, right? So why is this so problematic? Why can't we directly interpret these coefficients? Well, the underlying reason is, again, I mentioned this in the previous video and here, is that ultimately these coefficients for the intercept and for our dichotomous indicator for gender represent extrapolations outside of the range of data that we actually observe. Okay, so this is now the fitted linear model with the interaction, where we extend the x-axis to 0, and we see basically height ranges between something around like 59, 58, something along those lines, inches, up to 70 something inches. Okay, so that's the range of heights that we observe in our sample. We of course have men and women. Men are on average tend to be taller. They also tend to have, if you look at within the range, obviously they have there is a gender pay gap. We have higher salaries for men, now obviously not controlling for education, not controlling for a lot of other confounding factors, but regardless of that, we do observe kind of higher salary for men in this sample. But the point is that the intercept, the kind of expected outcome for both for women and men is the expected outcome for height being equal to 0. Obviously, we don't observe this, and so these coefficients themselves are not interpretable. Okay. Now, how can we remedy this? The first thing we can do is, of course, we can rescale the outcome and center the predictor in order to make our coefficients more directly interpretable, right? And this is what we've done here. We now predict earnings in thousands of dollars, in $1,000, and we look at mean centered height. Okay, so we create a new variable, earn_k, which is just the yearly salary divided by 1,000, and the centered height, which is just the individual height minus the sample average. We run the same model now with earnings in thousands and centered height, and now we have obviously coefficients that are directly more easily interpretable. Okay, now the intercept is the expected average yearly earning for women of average height. Now, if we're really kind of precise about this, there's still a problem with this, because obviously men and women have different average height. This is the average height for like across men and women. So essentially this would be, although we're kind of looking at the expected outcome for women for average height, since this is the average height over the entire sample, this would be the expected outcome measure, so the expected salary for quite tall women, actually. Okay, so if we're really precise about this, we would, we could potentially kind of think about taking into account different averages for men and women as we interpret this, for example. But for now, this is fine. We have an average height, at least for the entire sample, and the expected outcome is 16.6, so $16,000 in expected salary, and that's the intercept right here that I'm just pointing out. Okay. Obviously, at this point, men or across the entire sample, we observe higher salaries for men. The difference for average heights is around $9,000 per year. So we have, rather than 16.6, we have around 25, a little bit more than $25,000 yearly average salary for men in our sample. Okay, and we see the kind of relationship with height, where we observe that for 1 unit increase in height, this is still measured in inches, so a 1 inch increase in height for women basically increases the predicted yearly income, the predicted yearly salary by around $380. So $0.38 thousand, so $380 per year, and this kind of increase is larger for men. As we can see, the slope here for men is slightly higher, so there's a stronger predicted difference between expected salaries for taller men as compared to shorter men. Okay. Obviously, again, as I mentioned, we can't directly give this a causal interpretation. Okay. All right. So this is kind of already makes interpretation easier, in the sense that we now can interpret the intercept. We can interpret the kind of main effect for gender, because it corresponds to the difference between men and women in the predicted outcome for average height, with the caveat again that this is average height across the entire sample, across men and women. But what if we kind of want to evaluate a little bit more? Okay, to what extent is this effect of or this predicted difference due to height comparable or larger or smaller than the differences that we observe due to gender? Okay, and so one way to address this question is to standardize the predictor. Here we're not only looking at the centering the predictor, but also dividing by 2 standard deviations. We could also just look at z-scores, but again, in order to make this comparison easier between dichotomous indicators and continuous indicators, we can also look at dividing by 2 times the standard deviation, and this is what we're doing here. I'm calling this height z for the z-score, but of course this is not a real z-score. We're dividing by 2 times the standard deviation, following the recommendation by Gelman in the textbook to make this comparison. Okay, same regression, and if you kind of compare these plots, you'll see that essentially all that's changing is here the scaling of the predictor. Note that the data points seem to be moving a little bit. The only reason why they are moving is that there's a jitter. I randomly kind of moved the points in each of the plots just to make overlapping points kind of stand out and to basically see all the observations. And so if this jitter wasn't included, then of course these plots would be exactly equivalent, right? The point is, again, the model fit is the same. We're just rather than looking at a 1 unit change as a 1 inch change in height, we're looking now at a 1 unit change that is basically a change from -1 standard deviation in average, -1 standard deviations in height to +1 standard deviations in height from the average. Okay, so from so that's a 1 unit change on this standardized predictor. Okay, is essentially a change in 2 standard deviations. Okay, and so now we can basically kind of roughly compare how much of a difference basically a 2 standard deviation change in height, how much of a difference that makes in terms of outcome, in terms of the predicted outcome, the salary. So if we increase, or a 2 standard deviation increase in height is associated with a predicted increase in yearly earnings by about almost $3,000 in yearly salary. Okay, compared to the gender difference that we observe, which is around $9,000 here for men as compared to women. So kind of based on this comparison, we would say that we could say that obviously the gender difference is more impactful than this difference by height. Okay, obviously the effect here of height, or the coefficient here for height, is the same for both models, right? Because we didn't change height, we didn't change the average itself, we just rescaled our predictor. Okay, so much about linear transformations and this particular example. As I mentioned, whenever we're talking about standardization, we can sometimes it's useful to make these comparisons in effect sizes, but there are disadvantages, particularly since the standard deviation is a sample estimate, and it makes cross sample comparisons potentially more difficult, right? So you should certainly not always, in every case, in every application, standardize your predictors. In some cases it makes sense, in some cases it wouldn't be advisable, particularly with small samples, and if you're interested in comparing substantive effect sizes across samples, essentially. Okay. All right, so this kind of concludes linear transformations. In the next video I'm going to talk about logarithmic transformations.